Okay, so I'm going to begin. So as I said in my quick talk, in my quick introduction, this talk is developer feedback. So we will see some a small line of code, but mainly big problems that we had faced with handling of big models, merging big models, transforming big models. So I said I will not introduce CDO, but I will do a quick introduction, one slide. Then explain the industrial context, the main architecture of our software, and then the main part is the problems and the associated solution that we found. So CDO, connected data objects. It's an OMF-compatible way to store and manage a model, its evolution and its variance. So there is mechanism like auditing, so you can go back in time and have a view on your models at this time. There is branching, so you can work on your own branch, modify your models, and that's all. Merging and diffing is not included in CDO itself, but all the basic bricks are here to do it. This is a translational framework, so you can modify your different objects of your models, and the set of this modification is kept, and you can go back in time with that. It's not file-based, you need a server to do it. And it's also fully lazy. The model is not loaded when you open the view, but when you iterate on the model. There you see some other stuff like live notification. I will not extend on that because we do not use it. It's more when you are doing live editing, like in OBO Designer. So the initial context. The goal of our software is to have a central architecture databases. These databases need to communicate with various tools to edit or analyze the data. For example, to do safety analysis or cost analysis of a trade of an architecture. These various tools have various format, EMF, UML, profile UML usually, XML. Some zip, XML in zip, ugly. And so we are heavily on the branching and versioning mechanism of CDO. And we will rely on the access control component of CDO too. Currently, we use it quite lightly, but it's our next step. So this is a quick overview of the branching model for the architecture. So it's not the same name, but it's the same thing as SVN or Git. So you have a main baseline where you put your stable architecture. When you want to test something, you create a branch. If you're not happy with it, okay. If you're happy with it, you want to merge it back to your main model, and perhaps some small variants of this model. So this is the architecture of our software. We have the CDO server. This is nearly a pure CDO server. We just put our generated models in it and some customization of the security model, but not much more than that. A lot of the logic is in the client. Currently, we are communicating with the tools using Exchange tools format, like I said, XML and stuff like that. At the end, we plan to provide directly a Java API, and perhaps later some bridge to other languages than Java, or some web bridge, a REST bridge. So currently, it's mainly with file, again. The files are processed, I read it first, then transformed using either ATL or Java. The client API is here mainly to hide the CDO concept. I have some a more abstract view with more usual stuff like commit. Only the main. We go over. Yeah. Okay, so our problem container. So first, we have a lot of the problematics are done with the IDs of the object. Why? Because the IDs of the central repository are usually not the same as the IDs that you came from the tools. And you usually can't force the tool's ID and or you can't unify all the IDs of the tools. So we need to keep mapping. So we choose to use client-side allocated unique IDs. Why? Because it's easier to work with the export form EMF standard format because they already use uniquely generated ID. The other solution is to use servers generated, which is faster because it's incremental ID integer, so it's faster to index and stuff like that. But you need to do a round trip when you create an object with a server to retrieve the ID. So you can play with the object ID before going to the server. When you have to deal with ID mapping between tools and the central repository, that's not an easy way of going. So cons slower and not the most used part of CDO. So we hit some bugs that will be detailed. During our use of these unique IDs, we found that there is no easy way to set the ID of an object. It's not that that's quite normal because it's even not supported in the normal EMF standard. It's somewhere in the XML resource implementation details. So we talk with Ike and work with him to write a patch which will set the ID of the newly created object. This will be highly useful when doing merging, because when you go back where you take an object, you create it back on the other branches, but it's a new object, so the ID is something random, and you want to set it to the same ID of the other branch. Otherwise, the next time you want to diff or something like that, they will not match. So when playing with this resurrect object API, we hit a primary key bug on the database engine, because when you suppress an object of a branch and you want to go back and put it again, there is a version which stays the same, so you can't go back because the primary key forbid it. Okay. So we choose to use EMFD merge as the motor to handle diff and merging. The main integration point was to use a newly introduction resurrect object to set the IDs. Since CDO provides a way to retrieve a non-tester of two different variants of the model, we use it. It helps the differ to do a merge when there is conflicts. Currently, it's not fully optimized compared to the CDO EMF compare integration, because the CDO EMF compare integration reuse some data from CDO. CDO can provide you a list of change objects between two commits. So you can take this change object and optimize the differ, so it can only go through this set of objects. that has not been done currently because of lack of time. And so more generally, regarding performance, as I said, usually what we do is model transformation, diffing, merging, all of that usually load the full model. It's not like when you are doing editing. Usually you want to edit one diagram for one part of the model. Here, everything needs to be loaded. Unfortunately, lazy loading is cool when, when it's needed, but when it's not needed, it's quite slow because you have to do one round trip to the server for each object loaded. So when you have 2,000 objects, you are doing 2,000 round trip instead of one network communication to load the whole model. So we have something in CDO called CDO prefetch that do exactly that. That prefetch the whole content of the CDO object. CDO object can be a resource. So you can prefetch a whole resource of an EMF model at once. We hit a bug here too. When you are doing that on a branch which is just been created, so which has nearly no modification from its branch point, the prefetch is fully ineffective. It was quite weird. It's the first time I see it. There is a bug opened and a patch thanks to OBO. So I took a little before of the ID mapping problem. So two lives there of generation pattern of IDs and referentials. So we need tables to map them. Potentially, it needs to be multiple mapping. For example, if I have some UML profile, I usually need to store two ID because I need one for the stereotype and one for the base object. And it's usually map only one object on the central databases, which is DSL based. This mapping needs to be common, so I can't store it on the client side. This needs to be stored on the CDO side. So first, I'll try to do it purely in EMF. So a mapping is composed of link. A link is many-to-many link between IDs. Quite simple. All the shift here are operation. That's for speeding up retrieving of link object. All these operations are map-baked to speed up a lot the operation. Problem is that maps can be quite heavy on memory. Usually in our software, we need to load 3 times a big model because with three-way merge, you need the target, the referentials, and the ancestor. So 3 model plus the various mapping table needed. That is quite heavy because I need like 4 maps to have back the operations. So what I do is I store the maps using soft references. So if the software runs out of memory, they are collected by the garbage collector. And the next time I call the operation, I complete the maps again, and everything works again. So that was a problem for memory, but we face also another problem, is that I create one link object for each model element. This is also quite heavy on the database. Since ID are quite unique ID are quite heavy, it nearly not double, but at least add up half of the models each time I create a mapping. Since the history kept, it's grow up quite quickly. To solve this problem, we thought that it could be useful to store this mapping in a serialized and compressed way. So as I said, we can't do it on the client side. so it can't be file-based. It needs to be stored in the CDO. And hopefully, CDO have a quite nice feature, which is text resources and binary resources. That's a shortcut in the EMF API that allow you to have unstructured data which is stored in the CDO repository. These resources can be manipulated easily with standard input stream, output stream in Java, for example. For example, text resources are already used in Papyrus to store CSS style sheet. And someone also used it to store the xtext resources in textual form, if I remember. So on the metamodel side, I tried to be as unobtrusive as possible, because it was already working. On the right side, I put operation instead of feature, but with the same accessor name, so the generated Java interfaces match. It helps me to keep low on memory because I don't have to have a fully object, but I stay compatible. The links feature is not stored anymore, so it's derived, calculated from the binary resources. So what do we gain? So we use a standard JSON for serialization and XZ to compress. We gain factor 300. Why XZ? Because I tried JZ before. And big advantage for XZ because unique ID are quite redundant. So 3 tips for implementation. So as you see, I talk here about deserialization and serialization of the tool mapping, but you need to call it sometimes in the workflow. So for the serialization, it's done. It's easy. It can be done right before commit, and we have a hook for that. As you can see, you have the name of the method on the transaction to add the handler. The deserialization was a little trickier. I had to study a little of the object states of CDO works. And I find that a loaded object change of states from transient to clean. So it was a good place to deserialize our binary resource into a full EMF compatible structure. And last but not least, disable notification, because when you are created the tool link, you are adding to a feature, and if you don't disable notification, your application thinks that you are really adding feature and not reading a model. Metamodel evolution. So this is the typical problem that is currently solved using M2M technology like at ATL. But in the CDO world, you have to deal with the history and the branches. So the first thing we try is with a very simple modification, like adding a feature or modifying the name of the feature. You can implement hooks on the server side that directly deals with the database abstraction and the mapping. So basically, it renames the SQL column, for example, or add an SQL column when you add a feature to Eclipse. Donc, on the good side, it's really fast, and it keeps the history clean. The problem is it's not really a model transformation. It's a small evolution of a metamodel, but you can't redirect some feature or stuff like that. You could perhaps do it with by analyzing the difference in the metamodel and convert it to some SQL queries, but it will be quite difficult. So the approach we choose is to migrate the branches, and to migrate because we choose to not keep the history in the case that we need the metamodel evolution. The full history. We could do it with the infrastructure with what I will explain, but it would take a lot of time because it would have to go through a natural transformation for each commit. So currently, we have, I take nearly the same schema as the first one. If you test this one, you need to first migrate. If you want to migrate trade one, you need to migrate the one branch point on the main branch. Then you can migrate the end of your branch. Each migration point needs a merge and a natural transformation, so that's quite limited. So here for only like 3 or 4 branches, you have already 7 migration to and merge. Authorization. This quickly evolved between Kepler and Luna. So we work on that on Kepler, which has a really basic security metamodel, which can handle the login, groups, roles, and permissions based on object type and resource container, but you can't say stuff like I don't want Toto to modify the object that is called system, for example. Hopefully this is extensible. There is a permission mechanism, so how it works. When a permission is hit, the Java interface is applicable is called. In is applicable, where you are receiving the object which is modified and the branch which is modified. And you are responding either read, either write, or no, I don't know if it's supported, I guess not. Either read or write, and to see if you can modify the model. So this mechanism is still available in Luna, but there is a much more powerful metamodel which provides exactly what I said before. You can say you can't modify an object that is called a system using expression. We have a work in progress in Atos, which is handle not only read-write, but also create, read, update, and delete. So most of our work is not available anywhere yet. But most of it is not dependent to the metamodels, so could be open source. Currently as a GitHub, I guess, and perhaps later as a Polaris project. Thank you.